So far we have studied the titration of strong acids with strong bases, and in that case that's the simplest case because the reaction is fairly simple. You can just write it like that. When you titrate a strong acid with a strong base, you're pretty much just neutralizing the hydronium. Actually, you can also write it like that. The reaction is still the same, just that in this case you'll have two waters. Notice that the proton can be either written explicitly or attached to water. In any case, the product of neutralization of a strong acid and a strong base is water. This means that when we draw the titration curve of a strong acid, the titration has a profile a little bit more abrupt than what we're going to see today, and the pH at the equivalence point is 7. Also, the pH is given directly just by the concentration of H3O+, which is equal to the initial concentration of acid. That was the simplest of the cases, because what we're going to do now is the titration of a weak acid with a strong base. And this would be a weak acid in water. Notice that it's in equilibrium, but mostly we're going to consider that when a weak acid reacts with base, there is no equilibrium. It reacts completely to the right. Okay, so please notice the difference. When the weak acid is alone, there is an equilibrium, and this equilibrium is actually explained using the Ka. But when you mix it with strong base, this constant, this is not Ka, this is much larger than 1, we can pretty much consider it to be displaced all to the right. However, there is the difference that notice that the product is not just water. Let me give you an example. If you are titrating hydrofluoric acid, which is a weak acid, with a base, now the product is fluoride, which is not a spectator ion, it's not a neutral ion, this is a base. Okay, so please keep that in mind, because that's going to change also the pH at the equivalence point, as well as how to calculate the pH at the beginning. So let's start with doing exactly this. If we titrate 10 milliliters of 0.1 molar weak acid with sodium hydroxide, what is the pH at the beginning? Notice that if this HA were a strong acid, the pH at the beginning would be immediate. The pH would be 1 because 0.1, you have the concentration of the acid is 0.1 molar, which is totally dissociated. That's not true here. This is a weak acid. At the beginning, before we add any base, we have this equilibrium up here. Okay, so how can we calculate the pH at the beginning? We have seen this before, so we just need to build the ice table for this weak acid. In this case, the Ka, it says that is 1 times 10 to the negative 5. Okay, so initially I have 0.1 molar, and the change is minus x, and there's going to be x and x. I forgot this. And the equilibrium is 0.1 minus x, x, and x. That is, the Ka is equal to x times x, that's x squared, divided by 0.1 negative x. This can be approximated, meaning this is a weak acid. You can assume x is much smaller, so you can say that x squared divided by 0.1. This is pretty much 0 compared to 0.1. Okay, so in other words, your x is root square Ka times 0.1, or if you will, the root square of 10 to the negative 5 times 0.1, the root square of 10 to the negative 6, that is 10 to the negative 3 molar. That is, the pH, x is the concentration of H3O+, this is 10 to the negative 3, the pH is 3. Okay, notice that even though we have an initial concentration of 0.1 molar, the pH is not 1 because this is not a strong acid. This is a weak acid, and we need to solve the ice table. So, sorry for the overlap, I guess I wrote too much. But that will be at the beginning. The pH will be 3 at the beginning of the titration. And what is the pH at the equivalence point? Well, first of all, what is it that we have at the end? At the equivalence point, we have added 0.1 So at the equivalence point, what we have is this. We have added, say that, let's do it in moles. Okay, so if you have 10 milliliters 0.1 molar, that means that you have 10 to the negative 3 moles. Okay, so you have 10 to the negative 3 initially moles. You have added at the equivalence point, you have added as many OH negative. Okay, that means at the end, no, this is not X, it's a completely displaced to the right. So what you have is 10 to the negative 3 moles. So the concentration of AH negative is 10 to the negative 3 moles, okay, because all the initial HA now is in AH negative, divided by the total volume. Notice that the total volume is 10 milliliters plus the 10 milliliters of sodium hydroxide that I added necessary to neutralize this. This is 20 milliliters, in other words 0.02. Okay, so this will be, I'll have to do it this way, times 10 to the negative 1, or in other words 0.05 molar. Okay, so what is the pH? If in solution I have 0.05 molar of this base. Let's keep, so what I have is a solution of 0.05 molar in A negative. What I know is that the Ka was 10 to the negative 5. Notice that the Kb is Kw divided by Ka, or 10 to the negative 14 divided by 10 to the negative 5. That is 10 to the negative 9. Okay, so let's see. I only have the conjugate base in solution, and the conjugate base in solution gives way to this equilibrium. Okay, notice that now it's a base. So initially I have 0.05. The change will be minus x plus x and plus x in equilibrium. 0.05 minus x, x and x. So the Kb, which I calculated to be 10 to the negative 9, is x times x, that's x squared divided by 0.05 minus x. I'm going to assume again pretty much that this is close to 0 compared to 10 to the negative 2, and what I have is x squared divided by 0.05. Therefore my x is the root square of 10 to the negative 9 times 0.05. Okay, or in other words, this is the root square of 5 times 10 to the negative 11, which will be around 10 to the negative 5 molar. A little bit more, okay? I do not have a calculator here, but if you do the root square of 10 to the negative 11, will be close to the, yeah, or something around like that, okay? Notice that this means that the pOH will be, again, around, if you do the logarithm of this, will be 5. That means that the pH is 14 minus 5, which is 9. Does that make some sense? So notice that if we were to draw the titration curve, volume of milliliters of NaOH, 0 molar, initially, so 1, 2, 3, let's say that 7 is here, I'm being generous, this is 8, this is 9. So initially I start at 3. Even though I have a titration of a 0.1 molar weak acid, I just calculated in here, that's overlap, remember, in here I calculated initially, I start the curve at 3, and then when I have added as many milliliters 0.1 molar to neutralize all of the acid, I will be at pH 9. Okay, so I start something like that and something like that. Okay, so different things change. compared to the titration of a strong acid. One, the initial pH has to be calculated using the ice table for the acid, and two, at the equivalence point, this needs to be used using the ice table using Kb. So this is using ice using Ka, and also calculate this. Has been diluted by half because we have added the extra volume, but so that there you go. It changes a fair amount. There's a significant amount of calculations more that need to be done when you are titrating weak acids with respect to strong acids. In the next video, we're going to calculate the pH around here, which there is a very convenient formula to do that. Hopefully it will not take that long.